Good morning, respected sir. My name is Pujita Krishnan, and I am here pursuing my first year in Electronics and Communication Department, Section B from Institute of Aeronautical Engineering, Dundigal, Hyderabad. Well, my roll number is 21951A0477. I would like to present my TED Talk presentation in the subject Mathematical Transform Techniques and PT on the topic the application of 2D numerical inversion of Laplace transform. So before getting into a presentation, I would really like to thank my department for giving me this great opportunity as it helped me in gaining practical experience and also getting knowledge on this topic. So let's get started with this presentation. Topic is application of 2D numerical inversion of Laplace transform. Introduction. In a wide of applications of physical interest, the Laplace transforms are used and for specific problems. The solution is sometimes expressed by numerous functions whose inverses cannot be inverted in the standard process of using inversion tables due to deficiency of the two-dimensional polynomial factorization theory. Therefore, the necessity of using two-dimensional, once again taking the arrow, yeah, the necessity of using two-dimensional numerical Laplace transforms and their applications arise with the intention to obtain effective unconventional methods to solving the mathematical models of interconnects, numerical inversions of Laplace transforms of one variable are strongly present in literature. After all, much less attention has been paid on two-dimensional transforms. Only a few methods are available in literature. This brings out the necessity to correlate and compare these methods together to be able to have a general overview and to emphasize potential methods for further development. So let us know what's the abstract behind this topic. Analytic expressions are derived for the eigenfunctions and eigenvalues of the Laplace transform and similar relationally invariant integral equations of the first kind. Some generalized concepts of information theory are introduced to show how the use of these eigenfunctions enables the maximum possible amount of information to be obtained when solving the inverse problem numerically. These concepts also explain how the amount of information available depends on the level of noise in the calculation and on the structure of the particular integral kernel. Some numerical examples which illustrate these points are presented in this presentation. So what are Laplace transforms? Let us know what are Laplace transforms. So these are the equations of Laplace transform given below, and where in this equation T is real and S is complex, and inverse requires complex analysis to solve. Note that transform f of t gives rise to capital F of S, where t is integrated and S is variable. Conversely, capital F of S gives rise to f of t, where t is variable and S is integrated. Assumes that f of t equal to 0 for all t is less than 0. So when all t is less than 0, then f of t equal to 0. So this is about what are Laplace transforms. So with these equations and the explanation. So why do you use Laplace transforms? Firstly, why do you have to use this Laplace transforms? So it can be used to find solution to differential equation using algebra, relationship to Fourier transform, allows easy way to characterize systems. No need for convolution of input and differential equation solution. Useful with multiple processes in system. So these are the reasons why we use Laplace transforms. So we have known how to why we use and what is that Laplace transform. So now let us know how to use this in our day-to-day life or in our mathematical form, how to use this Laplace. So it is used to find differential equations that describe the system. It is used to obtain Laplace transform, perform algebra to solve for output or variable of interest, apply inverse transform to find the solution. These are the ways how the Laplace transforms are used. So let us know what is inverse Laplace transform. Inverse Laplace transform is if L of f of t is equal to f dash of s, then f of t is called inverse Laplace transform of f dash fx and is denoted by L inverse places f dash f of x s equal to f of t. So this is inverse Laplace transform formula. So let us know what are the properties of Laplace transforms. Properties of Laplace transforms enables us to find out Laplace transform without having to compute them directly from the definition. The properties are given. The linear property. So first property is the linear property. Laplace transformation is a linear operation for functions f of t and g of t whose Laplace transform exists in constant a and b. The L of a of f of t plus b of t, g of t equal to al f of t plus bl g of t. So this is a linear property, which is the first property of the Laplace transforms. Going to the next property, it is also used in differentiation. According to this property, L of L df of t by dt equal to S Lf of t minus f of 0. It means that inverse Laplace transform of a Laplace transform multiplied by S will give derivative of the function if initial conditions are 0. Next property is n-fold differentiation, and this is the equation of the n-fold differentiation. The one which is given below this is the equation of the n-fold differentiation. So moving on to our next slide, what is time shift? Time shift is also a property of Laplace transform, where the Laplace transform of f of t delayed by time t is equal to Laplace transform of f of t multiplied by e power minus st, that is L of f of t minus t into u t minus t equal to e power e minus st f of x is where u into t minus t denotes the unit step function which is shifted to the right in time by t. So this is time shift. The next property is S-plane frequency shift. So this is the equation of the S-plane frequency shift. So this is an example based on this S-plane frequency shift, and this is the proof behind this formula. This is S-plane frequency shift. Our one more property is multiplication by t power n. L of t power n f of t equal to minus 1 of n into d power n by ds power n f of x. So this is the example based on this multiplication by t power n, and this is the proof of this formula. Proof given for the formula. So let us know what is the mathematical model of two-dimensional numerical inverse Laplace transform. To start off, let us begin by presenting the main definition of two variables Laplace transform equation. So f of s1 comma s2 equal to limit integral limit 0 to infinity, again integral limit 0 to infinity, f of t comma x into e power minus s1t minus s2x dt dx. So this is the one equation of Laplace transform, two-dimensional numerical inverse Laplace transform, where j equal to root of minus 1 is the imaginary number. Price are considered by researchers to be among fast computational methods. Nevertheless, these two methods were significantly improved by use of accelerating algorithms, which are described in the following sections. The symbols t and x can be generally any two independent variables, though due to our interest in engineering related applications, we consider them to be time and space variable respectively. The third method is based on Zackian's 1D NILT and uses the pad approximation for representing the exponential kernel. Accelerated FFT based 2D NIL. The method denoted as FFT based Epsilon 2D NIL is developed originally by applying the trapezoidal rule of integration into the definition integral with specific frequency steps given as ohm. So what is NILT? NILT is exactly our topic, which means numerical inverse Laplace transform, which is known as NILT. So when I equal to 2, I by n, where I equal to 1, comma 2, and by considering the original and discrete are sampling periods in the real-time domain with suitable approximation of the inversion algorithm and basic assumptions. What are the calculation steps? So these are calculated using up to n. 1 terms by FFT algorithms, where n and I is a free parameter that could be optimized for best results. By performing several tests in 6, it is shown that optimal number of terms used for the evaluation of the FFT algorithm were 512 terms. Furthermore, the remaining terms are NI terms are integrated with the T algorithm to accelerate the convergence and increase the accuracy. So let us look at the evaluation of 2D NILT methods. So these are the evaluation based on which the two-dimensional numerical inverse Laplace transforms methods are available. So this is the four methods or four ways in which the two-dimensional numerical inverse Laplace transform can be done by. So moving on to our next slide. Yes. That's the end of my presentation, sir. Thank you for giving me this nice opportunity and also for sparing your valuable time to listen to my presentation patiently. I am looking forward for a positive feedback from your side as your feedback really matters to me to do much better next time. Thank you, sir.